Einstein gave us a cosmic speed limit, the speed of light, approximately 299,792 kilometers per second. No object with mass can reach or exceed it. It's not just fast. It's the boundary that shapes our universe's structure. But what if something doesn't just break that rule? It was never bound by it to begin with? That's where tachyons enter the conversation. Unlike photons, which travel exactly at the speed of light, or particles with mass, which travel below it, tachyons would exist only above the speed limit. In fact, tachyons can't even slow down to light speed. They exist in a separate regime altogether. This flips our understanding of physics upside down, because according to the equations of special relativity, as an object approaches the speed of light, its mass approaches infinity, and it would require infinite energy to go faster. But the same equations allow for imaginary mass when speed is greater than light, and that's exactly the mathematical signature of a tachyon. Physicists call this space-like motion, trajectories that lie outside the light cone of relativity. This means a tachyon's world line cannot be connected to ours through any slower-than-light interaction. But here's the twist. The math doesn't break. It just becomes stranger. Instead of being disallowed by Einstein's equations, tachyons are a legitimate mathematical solution, one that lies on the other side of the light-speed barrier. So why haven't we seen one? The problem lies in measurement. Tachyons, if they exist, would behave unlike any known particle. They would gain speed by losing energy and slow down by gaining energy, the exact opposite of normal matter. This inverse relationship makes them unstable in our observable framework. They might emit energy indefinitely, a process that some physicists argue would cause them to instantly decay or vanish from normal spacetime. But others disagree. They propose that tachyons could form a hidden sector of physics, completely decoupled from standard particles. Like dark matter or dark energy, tachyons may interact only through gravity or quantum fields, making them invisible to all current detectors. Some theorists even speculate that the neutrino, a nearly massless particle, could have tachyon-like properties under certain conditions. In 2011, the Opera experiment in Italy created global headlines when it appeared to detect neutrinos arriving faster than light. For a brief moment, it looked like Einstein had been overturned. But within weeks, a faulty fiber optic cable was discovered, and the results were retracted. Still, the incident reminded the world that faster-than-light anomalies are worth investigating. If tachyons exist, they could explain more than just speed. They might unlock the mystery of quantum entanglement, where particles separated by vast distances appear to affect one another instantly. This non-locality has baffled scientists since the Einstein-Podolsky-Rosen paradox in 1935. While quantum mechanics accepts entanglement as fundamental, no one really knows how the information is shared. Could tachyons, unobservable but ever-present, be the missing link? Could they transmit correlations at superluminal speeds while staying hidden from our detectors? This wouldn't allow faster-than-light communication, since the outcomes are inherently random, but it could still tie together different parts of reality in a deeper, invisible way. Of course, this opens the door to speculation. Science fiction has long embraced tachyons as messengers from the future, as the engine for time travel, as the key to interstellar communication. But modern physics treats them with caution. In most quantum field theories, tachyons appear only temporarily, as signals of vacuum instability. In this view, they aren't real particles, but flags that a field is about to shift into a new state. Yet in some Lorentz-violating models, theories that allow small departures from Einstein's symmetry rules, real tachyons might still exist. They wouldn't violate causality in those frameworks because time, space, and information flow differently there. In fact, in the context of the emergent gravity hypothesis, where space-time itself is not fundamental but arises from deeper quantum networks, tachyons might behave like excitations in a more abstract structure, like ripples on a lattice of information. From that perspective, the speed of light is not a cosmic limit, but an emergent property, and tachyons may simply live above the layer we can see. Think of them like ocean waves that exist far below the surface, detectable only by indirect ripples in the deep. In this way, the tachyon becomes more than a particle. It becomes a conceptual bridge, connecting Einstein's rigid space-time with a more fluid quantum foundation. A whisper that says, there may be more than one kind of reality. And as our tools evolve, as we push further into quantum computing, gravitational wave astronomy, and deep field cosmology, we may one day glimpse evidence of that hidden domain. A place where particles outrun light, time folds in strange directions, and causality flows like a river with forks unseen. Until then, the tachyon remains both a mystery and a muse, an invitation to think faster than light.